So I said an antiderivative instead of the, and that's because the antiderivative, unless you have certain constraints, isn't unique. And I'll talk about what I mean in a second. But this is the start of something beautiful. Theorem. This is the start of calculus 2, so.
Hey yo, this is only calculus 1, dude.
Okay, if f is an antiderivative of little f, on an interval I, the most general antiderivative of f on I is, I don't want to do that anymore. Capital F of x plus an arbitrary constant c. So we'll just say where c is some real number. That is called the most general antiderivative by this theorem. It's the most general one you can get. Why does this make sense? Does anyone want to think about it? As to why defining the antiderivative in this way makes sense. Again, basically you're asking, what did I take the derivative of to get here? That's what the antiderivative is.
What is c?
It's just some number.
Constant?
So what did I take the derivative of to get here? That's the question, right? So let's try to motivate this with just a quick example. Suppose I have f of x equals x squared. I want the most general antiderivative of this function. So I need to ask myself, what function can I take the derivative of to get x squared? So you're thinking backwards here. What function can I take the derivative of to get to x squared? It's not necessarily obvious right off the bat. You could probably sit here, we could probably spend like 15, 20 minutes sitting here thinking about it, but I don't want to spend that long. Well, if you know the rule, it's not that hard.
What was your question?
What function can I take the derivative of to get x squared? So I'm thinking backwards, right? I don't have the function that I'm taking the derivative of. I've already taken a derivative. It's like me coming up here, taking a derivative, and then erasing the original function, and you not seeing it, and me asking what was here.
So that's the derivative that's
Yeah.
already taken?
The derivative's already been taken.
What was the original function?
Exactly. How do we
There
find
was
that?
nothing.
That's exactly what the antiderivative is.
Because if it was, it'd be like x cubed,
Okay, that's a good start.
but it can't because there's no 3 in front.
Okay, so how do we compensate for that?
Minus 3.
No.
Divided by 3. Ooh.
Okay, but by this theorem, we need to throw in an arbitrary constant. So we're going to throw that on.
0?
Just throw on C.
No.
You just literally throw on C. Why does this make sense? Why does this arbitrary constant make sense?
This can be any constant.
It can be. And if I were to take a derivative of capital F here, what would happen to that constant?
It would be a plus positive.
Plus what?
Something.
What's the derivative of a constant?
1. Nothing. 0.
Nothing. And so it would just go away, right? And so how do you know what this constant was if you weren't given any other information?
X.
It could be a 1, it could be a 3. Like I could come up with an infinite number of capital F's here whose derivative is little f. Because the derivative of a constant is 0. That's the fundamental reason we need this plus c. And so when you take an antiderivative, you have to always throw on plus c. Is everyone okay with that? Good. Let's do another. I don't know if I'm going on with this. This is example 1, by the way. So I have f of x is sine. I want to know what capital F of x is. Make sure I'm not going off the. No, I'm good. Well, can I take the derivative of to get sine? Makes your brain hurt a little bit because you're so used to going the one direction. Now go the other.
I don't know. Wait. Cosine. Negative cosine.
Plus
C.
Good. You have to put that plus c. If you don't, then it's like forgetting the negative on something. That's how wrong it is. Okay, because later on what we're going to be doing is figuring out what this c is based on some other information.
Is that why we need this?
I gave you that just as a reference, so you can kind of start organizing stuff in your head. You really only need up to the back of the second page. The rest of it is calculus
I've
too.
never seen any of that in my life.
This stuff, yeah, because that's 4.7. This stuff, and we're here right now. We're getting there.
We're on 4.9.
Yeah, no, we're getting there. We're getting to this stuff right now. That's what we're getting
Why
towards.
are we going backwards? You said that was 4.7.
It is. Most of the time, this is before this. I don't know why it's not here. Because this actually, the reason this is the right direction is because this actually defines this and the rest of it.
Did you video 4.7 or something?
I'm gonna put one up, yeah. I'm not necessarily gonna do one video anyway.
We're gonna put some random person again.
2. So x to the n for n not equal to 1. We're going to go ahead and prove a rule here, I suppose. This is actually a theorem. So how do we find the antiderivative of x to the n?
X to the n plus 1.
Okay, what else?
I don't know, it's kind of just guessing there.
Compare it to what we did over here. Right, n is just 2 in this case. What did we do?
We just added the 1 and then divided it by that number, so plus n plus 1. Or divided by n plus 1.
Plus the constant, right? There's you an antiderivative law.
You didn't see that, but I have
Yeah, there's an antiderivative law. So if you want to take any term of a polynomial, or any single term polynomial, and find its antiderivative, you add 1 to the exponent, divide by the exponent. It's the opposite of what you usually do when you take the derivative, right? With the derivative, you bring the exponent down, subtract 1. Here you're adding 1 to the exponent, dividing by that exponent. Okay, so this is the first big law to memorize. And again, remember what you're seeing.